but maybe we don't need it today. We'll see. Any questions? Okay, good. Thank you. So, I'll try to get them marked before your exam. But I'm gone for Monday and Wednesday of next week. There'll be no classes, and I'll be back Friday, so we will have a class, and we can have a review session if you want, and the exam will be the Monday after that. Okay? Any questions? No, I don't have it. You've done 5 so far, right? Yeah, I'm aiming for about 8 or so for the whole course, so we will have 3 more on the control aspects once we finish the midterm, second midterm. So yeah, 1 week without any homework, you can concentrate on studying. I have put one of the past midterm exams, so you can take a look at it and use that as a practice. Any other questions or comments? So in the last class we did 1 problem, so we're going to continue to do a couple of more problems today, and then I move on to the next topic of looking at transfer functions for valves. Valves are one of the most commonly used process units, so I'm not sure whether we'll get that far, but we'll see how far we can go. The next problem is a parallel system. Okay, so can you? Is this becoming weaker? Just a loose connection here. So what you have here, there are a couple of examples where you might end up with 2 systems that are seeming to have a parallel interaction instead of a serial interaction. So on the top left side, you see 2 valves. One is a bypass valve. Okay, so you have a heat exchanger, and there is a main feed to the heat exchanger. But when you want to control the flow over a fairly wide range, it's common to have a bypass valve. Okay, so we're just looking at these 2 transfer functions, a main valve and the bypass valve. So if I have the transfer function for those as G1 and G2, they are essentially acting in parallel. And the question is, what is the relationship between the output Y and the input X? Another example where you will have a parallel transfer function would be when you have reactions. Okay, you're going to be going to see in series or in parallel. So in such systems, you might end up with 2 equations that eventually can be represented in this block diagram. So our task is to find the effective input-output relationship. The effective input-output relationship, assuming G1, G2 to be first-order systems in parallel. How would you do that? So yeah, so you need to, the standard recipe, if you like, should be to find out the relationship between the input and the output for every block. Isolate the block, find out what is connected to on both sides, and write down an input-output relationship between those 2. And if you do that for every block, you will get a set of equations. And then it's just a process of elimination to get the transfer function between Y and X. Our ultimate objective is to get a transfer function between Y and X. Would you put? A valve, like a control valve. Typically, when you have a bypass valve, one of them will have a control action on this. The other one is basically to regulate total flow from one range to another range. If you want to operate on high flow rate regime, for example, you shut this off completely and let all the liquid flow through that. Okay, And over that high flow regime, you may want to control it. So the control action will be on this valve, okay? And then when you want to switch to a low flow regime, then you would have a bypass opened at a certain level, but still the finer control will always occur through this. In an on-off situation, right? So the second valve, the bypass valve, is either on or off, or at one fixed flow rate over a range of flow rates. That would be a typical scenario that I can envisage. I've not worked in chemical industry, so my practical experience is very limited. But yeah, right. So this is just an example of where you might have, but your question is legitimate because when I'm trying to write an effective transfer function, the second transfer function here is not really active except setting a certain level, okay? So it's going to be maintained constant. It's not going to introduce a lot of dynamics into the process, except when I make a change, the dynamic interaction will be there. Manual, exactly, right. That's what I would expect. That's you're confirming that. So very good. Do you have industrial terms that you've spent some time? That's actually good. You guys are required to go and work?
Yeah.
Not required, but it's kind of recommended because it's hard to get a job.
Right. I was in Alberta for 25 years, and there they had something called a co-op program, which takes 5 years instead of 4 years, and there are 5 work terms, 4 months each. So you're supposed to go and work there for 4 months and then come back and continue the study. And that occurred after 10 years I was at Alberta. I could see a remarkable change in the class, because when I say something, they can relate to it. They've seen it in the class. Before that, it was a 4-year straight program, and they have no clue as to relate the personal relationship in terms of, they've not seen a distillation column, right? So if you go, I went to this education where I didn't have co-op. I didn't go to work. So my knowledge is only theoretic completely. Okay, so it is very nice to have that kind of an experience so that you can relate. Whatever you're saying is not just abstract. Yeah, in the co-op program they have all year round. So it still takes 5 years for them to finish because they have 5 work terms, 4 months each, so 20 months. And so they are engaged in the second, third, and fourth year summer months, plus an extra. So that gives them 12 months plus 8 months extra. Summer, right. But you don't have a lot of time on summer, right? It's only 2 months, 3 months, 12 weeks. Right. There it was 4 months. But the term itself is 4 months. September to December, January to April, May to August. That could actually be dangerous. They have control on both of them. They just calculate with each other, one trying to annul the effect of the other, right? So that will, except in an on-off situation, that will be a good thing to do. Okay, any other questions? So the question is, find out y divided by x, the effective transfer function. I call it as GE. Okay, so how do I do that? I'm going to call this as x1 and x2. The output from the first block as x1, the output from the second block as x2. So, but x is the same thing that feeds both of them. Okay. Okay, so this is x and this is same x because it's the same signal that is split. Okay, so the same signal that is going to both, so x is the same, and x1 and x2 are the output from each one of them. So x1 is going to be equal to g1 times x, and x2 is going to be equal to g2 times x. Okay, so now next look at what happens at the summation. So these two signals, x1 and x2, are added up. So y is equal to x1 plus x2. So these three equations are arrived at by looking at the structure of the diagram and what happens between the input and the output of each element. And there are three elements here. G1 and G2 are the two blocks. The third one is the summation element. Okay? So you need to look at each one of them. So around the summation element, we get this equation, y equals x1 plus x2. And each one of the blocks, we get x1 equals g1x and x2 equals g2x. So all I need to do is now eliminate x1, x2. I don't need that. I need only the relationship between x and y. Okay? So this is going to be equal to g1x plus x2, which is g2x, which is equal to g1 plus g2 times x. Okay? So y divided by x is simply g1 plus g2. If it was series, it would have been g1 times g2. Okay, if the two processes g1 and g2 are in series, then the effective transfer function is the product. But when they're in parallel, it is the summation of those two. Yeah. We are dealing only with linear systems or linearized systems. Yeah. You have to linearize individually. Right. Yeah. Yeah. If they are interacting systems, then each one influences the other. One influences the two, and two influences the one. Then we will get a coupled set of equations. That is, the first equation will have both x1 and x2. The second equation will have both x1 and x2. You need to go for simultaneous solution, which you have seen and you have done in an assignment. Right? So if it is a truly interacting system, both ways, x1, x2 affecting each other, then you will get a coupled set of systems. Okay? If it is only a forward interaction that is series, then you get a product. It's easy to eliminate the intermediate one. If it is parallel, then you get the summation. Okay? But the systems can be much more complicated. I mean, you just have to look at a PFD diagram of any chemical plant, and you will know how complicated it is. So you need to be able to break it up individually and then analyze each process unit with its control systems and what feeds it in and out. Any questions on that? It's a fairly simple one. The next one is, and there are no numerical ones. I could put a numerical problem on this, saying I give you a G1 as a first order system with its time constant, G2 as a first order system with its time constant, then develop the step response, for example. Okay? So in this problem, they're not asking you to do that. The next example is a bit more complicated one. This is coming from a recycle stream, and recycle is very common in plants. Okay? So you are given directly the block diagram. Sometimes I may just give you what the recycle flow sheet is. From that, write down the block diagram. That would mean take the flow sheet, write down the equations for each unit, and see how they are coupled to each other. So here what is happening is there are three blocks and one summation unit, and you have identified all the, again, can you see it clearly? Okay, so the first block is G1, which relates T0 and T1. Okay, so we are going to write down each one of these equations. Okay, so the relation, so basically it says analyze the dynamics for a step change with and without recycle. Okay, so that here we have given all the numerical values. Okay, so we need to be able to do the problem and get a numerical answer. And with and without recycle basically says that with G2 as being 0.3 with the recycle, or 0 without a recycle. Okay? So if I make this as 0, then there is no recycle. Analyze the dynamics of that. And when I say analyze the dynamics of that, what do I mean? The output here is T4, and I want to see how that changes when I change the input by a step change. Okay? Do you have an idea of how you would proceed? Basically, the first thing is you need to get this effective transfer function, assuming that there is a recycle, and then it's very easy to turn off the recycle by just turning that off, turning off GH2. Okay? So how would I begin? And you can expect one question in your second term of this type, where I give you a block diagram and ask you to do an effective transfer function, and then look at the dynamics. Yeah? Label each string. We have labeled all of them, so maybe you need to label something. Write the equations for each one. So if I take, for example, T1 to T0, the very first block, I'm looking at this block. Okay. So the equation would be T1 is equal to GH1 times T0. Okay. So that is the input-output relationship. Then take this block. What would that be? T4 is equal to GR times T3. Okay. And the next one, take this block, and that's going to give you T2 as equal to GH2 times T4. Anything else we need to do? Then this block, and that is just a summation, so T3 is equal to T1 plus T2. So these are the four equations, but what I want is I want to get rid of T1, T2, and T3 and relate T0 only to T4. Everything else I want to get rid of. Okay? So now it's an algebraic manipulation. Okay? So what I'm going to do is I'm going to take T4 is equal to GR times T3. Okay? So I take this T3 and substitute for that. Okay? So that's going to be equal to T1 plus T2. Okay? And then I'm going to take T1 and T2. I have there. And I'm going to substitute for those in here. Okay? So that's going to be equal to GR times GH1 T0 plus GH2 T4. Now, is this an interacting system or a non-interacting system? Already you can see T4 appears on the right-hand side and on the left-hand side. So T4 is affecting itself. That would be a characteristic of any recycle. Okay? Any loop that you have. Even simple feedback control has that feature, and here also you have the same thing. Now, what else do I need to do? Rearrange. So collect all the T4 to the left hand side. So T4 times 1 minus GR times GH2 equals GR times GH1 times T0. Okay. So T4 minus, divided by T0 is GR times GH2 divided by 1 minus GR times GH2. 1, thank you. That is the effective transfer function GE. Okay, so it's fairly simple algebraic manipulation, and unless it's a truly interacting system, when you write these equations, you will find that both equations have both the variables. Then it calls for simultaneous solution. But in a situation like this, it's normally sequential with the recycle, so you can eliminate fairly easily and get the effective transfer function. Any questions on that? So now I need to substitute all the known transfer functions, and this is where I guess I need to go to MATLAB because there is an important point I wanted to show. Maybe I can just show it by analysis, and I can let you do that math. We'll see how far we can go. Okay. So now GR is given as what? GR is 3 divided by 10s plus 1. Multiplied by GH1. GH1 is 0.4. It's a constant. Pardon? Oh, I'm sorry. Yeah, I'm sorry. Are you able to see it now?
Yes.
Okay. Okay, divided by 1 minus GR, which is 0.3, divided by 10S plus 1, multiplied by GH2. GH2 is given to you as 0.3 or 0. Okay, so it's going to be 0.3 with recycle or 0 without recycle. Okay, there are two cases that you need to look at. So case A with recycle. Okay, so GE is then 1.2 divided by 10S plus 1 divided by 1 minus have to push it back there. Okay, so let me just take a common factor there. So it's 10S plus 1 minus 0.9 divided by 10S plus 1. Okay, so the 10S plus 1 will cancel out, and what you're going to get is 1.2 divided by 10S plus what? 0.1. Okay, or you can write this as multiply and divide by 10, so you can write this as 12 divided by 100S plus 1. Okay, now you can see that there, right? Okay, so case B, without recycle, what would happen? GE for this case is going to be, this is 0. Okay, so it's going to be simply 1.2 divided by, are you with me or not? 10S plus 1. Now, if I ask you in an exam a question, well, you should be able to invert this. This is just a first order system, right? So I Laplace or look at the table and answer further questions on how long does it take. But by simply looking at it, I'm asking you the following question: which is going to be more sluggish, with recycle or without recycle? With recycle, right? Because its time constant is of the order of 100. So if you make a step change, it's going to take 100 minutes for it to reach 63% of the steady state. Okay? Whereas without the recycle, it responds much more quickly. Within 10 minutes, it will reach the same 63% of the final steady state. Okay? Any questions?
What if it was one, like the 1,012 over 100 at some point? What if you don't do that?
That's what I was.
I look at the play one as one.
Right. Why do I? That's a very good question. Why do I have to write it as tau s plus 1? Why can't I? That's the format for the inverse. Okay. So it is tau s plus 1. You need to have that 1 there, and then only the tau gets the meaning of the time constant. Because when you invert it, you will get e to the power minus t over tau. Right. So you need to rescale this. You cannot just leave it like that and say my time constant is 10. It's not. You need to rescale it such that this coefficient becomes 1, and then this gets the interpretation that it is a true time constant for a historic process. Of course, all these dynamics will change if I change the two transfer functions that were constants, here 0.3 or 0.4. If I make them first order, then the net second order effect and third order effect you will have. Okay. So the concepts can be checked using very simple first order thing but a complicated structure. So in this problem, we are just learning how to analyze a complicated structure, but by making these transfer functions just constants, we are simplifying the algebraic manipulation. Well, if there is no recycle, that is, if there is no energy or material recycle, this stream is out. That stream is out. The transfer function is out. By setting that equal to 0, you don't have any feedback of information through the recycle. Basically does that. In any process, the recycle takes the information from downstream and feeds it to upstream. Yeah, it simply becomes a product of, right, yeah. 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 Right. Yeah. That's a good observation, yeah. Yeah. That's a gain, right. Process gain, right. The net gain of the entire process, because it is with the recycle, right? So the net gain, yeah. The process here itself will be only GR. Okay, this is the process, and well, you can consider this whole thing as an effective process. And the net gain between the input and output is going to be different. Yeah. So any questions? Do you feel comfortable with that kind of a manipulation in an exam? Yeah. Well, right. When you are writing a transfer function, typically you write it as a gain divided by a time constant times s plus 1. Okay. So this is called the gain for the particular transfer function.
Oh, so once you scale it from 1,
Then numerator is the case, right? Yeah. 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 Okay, so all these problems that we have seen this week, plus the problems that you did in your 2 last assignments, make sure that you feel comfortable with doing problems for that time, okay, or your second midterm. Now, let's talk about control valves and how would I model them and how would I develop a transfer function for them, and then a control action on that. Now, here I have given you 2 graphs. Okay, 2 pictures of control valve. Study that and tell me what difference do you see between those 2. One is labeled air to close, the other one is labeled air to open. What are the differences in the way that they would function? And then we'll talk about when you would use them and what conditions you could use one of them. Exactly. So everybody got that? It's a pneumatic signal. As I told you, even these control thermostats are pneumatically driven. So you send a pressure, okay? So when you pressurize this chamber, it's going to push this down. So it's going to push the valve down. When you push the valve down, what happens to the valve? You have to study carefully what is happening here, because of this shape like this, as you push down, it's going to close. Okay? So there is an opening, and through the opening, the liquid will come through this, and through this opening, it's going to come out and go like that. Now, if you shut that, you're shutting it. Okay? So this is why we say it is air to close. So when you apply the air pressure, it closes. Now, if you look at the other one, when you apply the air pressure, the same mechanism. It's going to drive this, it's going to drive this, but the valve itself is inverted. Okay, so it's going to open. When you apply the pressure, it's going to open. Why is this important? Is the next question. Fail close. That's it. You got that? Then you have some idea of the safety concerns that one has to use in picking these valves. Okay. So it's basically from safety consideration. The dynamics of it is typically captured by the same equations for both of them. Okay? So the transfer function between the input and the input being the air pressure and the output being the percent opening or the flow rate. Okay? So that transfer function will remain the same for both, but one is going to remain open in the fail state. Fail state meaning you lose the power supply. What happens when you lose the power supply? In the first case, it's going to remain open. In the second case, it's going to remain closed. Okay. Now, if you had exothermic reactor, to that you are supplying the coolant water to keep it cool. which one would you use? Which valve would you use? Air to close, because if it fails, you still want the coolant to be flowing. So if it fails, you want the valve to remain open so that it will still supply, so that the reactor doesn't blow up. So it creates energy, and you need to remove that energy. Where would you use air to open? Normally in toilets, right? If you go to the airport and if you're putting your hand, it lets the water flow, right? And if there is no air supply, you don't want the water to be draining all the time, so at least completely shut it off permanently, right? That would be one example of that. Okay? So safety considerations are the ones that allow you to choose between these two, but the dynamics is going to be basically the same. Any questions on that? So the dynamics is between the flow rate and the pressure, air pressure to the valve. Okay? So as you apply more pressure, you open it, for example, then you have more flow rate through that. And that can be modeled typically by a first order transfer function. Okay? So Kv is the gain for the valve, and tau V would be the time constant for that one. Typically, these valves, what do you think? How long does it take when you open or close? What time constant are we talking about? The time constant for the valves to close or open. Okay, that's going to be extremely small, of the order of microseconds. Okay, so the same thing, like in the thermocouple, often if tau is of the order of 0.3 millisecond or something, you can ignore that and say 0. Okay, so often you'll find that the approximation to the transfer function is that there is a gain. You need to know the gain. What is the importance of gain here? It takes care of the conversion of units. Remember, you have to have consistency in units. So the signal that is coming to the valve is in terms of PSI, and the signal that goes out of the controller in this block diagram in semi-link will have the units of flow rate, meter cube per second or foot cube per second. Okay? So K should absorb that difference in the units. It should be consistent. Okay? So this would be a typical process flow diagram where you have the transfer function for the valve and the transfer function for the process. The input signal is P. Here you will have Q. Here you will have Y. So the gain for each block will take care of the differences in units between the input and the output. Gain will absorb that differences in the units. Okay, so that would be the effective transfer function for a process with a valve attached to it, where the valve time constant is so small that we can ignore that. So we just have the gain for the valve. Now, how would a proportional controller for the valve look like? How can I model that? Okay, so I guess we have seen it like this in terms of deviation variable. P minus PS is equal to Kc times epsilon. Epsilon is the error signal between the set point and the actual flow rate. Okay, so the proportional controller basically says that the pressure signal that I need to send is proportional to that error signal, Kc being the proportional constant. And that equation is rewritten in this case as P equals Ps plus Kc times epsilon. Okay, so the transfer function for the valve, for the controller, is going to be P divided by epsilon. The error is equal to Kc, proportional controller. Now, is that true? In practice, can I have an error signal that is coming to the valve and I adjust the pressure indefinitely? Because what this is saying is that the pressure change is proportional to the error. Proportionality constant is the controller gain. Okay? But if I graphically represent this, it's going to look like this. Okay? So this is the true pressure, not the deviation pressure, lowercase p, against the error. So when the error is 0, there is some steady state pressure Ps. And we call this as the bias value. Okay? And when the error is not 0, the pressure that you apply to the valve is going to be determined by that equation. P is equal to Ps plus epsilon times Kc. That's an equation for a straight line. Okay, so that is this line with a slope of Kc, which is a controller gain. Okay, but the question is, will that kind of a transfer function work for a real valve? And the answer turns out to be no, because the valve will saturate, meaning there is a maximum limit at which the valve will stop increasing, opening further. Similarly, the lower limit also. So these are called saturations. So the real transfer function should capture a behavior like this, where it shuts off. It has a linear response. The controller has a linear response over a certain range, and then it will shut off. This is why we saw that need or the ability to put step functions, ramp functions, and construct more complicated input is useful in Simulink, for example. Okay? Or to break it down in terms of Laplace transform for each one of these. So the ability to build such forcing functions or representation is important. Any questions on that? Okay, so in real life, the valve cannot open large and larger extent forever, so there are practical limits, and this is what we call saturation. Now, what is an on-off valve? Simply says the valve is open or closed. Okay, how would the transfer function for that look like? It simply says that if the error is positive, open it fully. The error is negative, shut it off completely. Okay, so there are only two states. It's often called the on-off control, and an ideal on-off control looks like this. This is the error, and if the error is greater than 0, you apply the maximum pressure to shut it off, for example. If the error is less than 0, you apply the minimum pressure so it opens fully. Okay, so the transfer function for that should be corresponding to a step change. Okay, now, is that a good idea? To have an on-off controller like that, where it opens or closes? How would such a valve behave? Now I'm asking you to kind of project your intuition. It will flip on and off all the time, because the error is not going to be exactly 0, right? It's going to be fluctuating around 0. Okay, so you open it, the flow rate increases, it affects the whole process, the error becomes negative, then it shuts off. So that is called chattering. Basically, it just flips back and forth at a relatively high frequency. Okay, so you don't want that. So what you want to do is, when you're defining this on-off control mechanism, if you choose to use that, you need to have something called a dead band, which says that only if the error is greater than a certain value, open it, and only if the error is less than a certain minimum value, close it. Okay, so in opening, it follows this path. As the error is in this stage, once it exceeds Emax, it opens that, and it will keep it open until the error falls back below a certain minimum. So while coming back, it follows this path. Okay, and as a control engineer, you choose what this dead band is, so that you don't have this frequent opening and closing. You want to control how frequently it will open and close. Okay, so this is what we are talking about are issues that relates to how to control a valve. What is the transfer function for a valve look like? And when I put a proportional control or on-off control, what are the problems that I encounter and how I can handle them? Any questions? Yeah. The PID, right. So it's not the valve, but it's a controller that's cheap. The cost of the controller, like PID controller, will be much more expensive than on-off controller that controls the valve. The valve cost is going to be the same, but what you will find is the valve design. If you're going to require only on-off, you will design the valve to be simpler, meaning you don't need, for example, if you go back to this valve, So now we are the valve manufacturer. Okay. So if you need the flow to be continuously changing as you change the height of this, a process requires that, then you would design this valve to have this tapper, right? So that as depending on the extent of penetration, you can control the flow rate. But if you want on-off, how would I change that? I would simply, I don't have all these complicated designs. All I need to have is something like this, a flat one. So it just shuts off. Or when it opens, it opens. So I don't need this tapered design there. Okay? So that will make it cheaper to manufacture for the valve. So when you are selecting your controller, you need to select the valve that goes with the controller and see which one meets your purpose. Okay. Proportional integral control. Okay. So now we're talking about controlling a valve. Okay. So the valve output is the steady state value plus the error, one part that takes care of the proportional response, the other part that takes care of the integral of the error. Okay. And always we have been writing this as simply Kc. The same Kc goes in both places, and this is tau I. But effectively there are two constants for a proportional integral controller that a control engineer must design or tune in an operating plan. You have to select what is the best value for Kc and what is the best value for tau I. So in terms of deviation variable, you would write this as P minus Ps, which is equal to the capital P, which is the deviation variable, as equal to Kc epsilon plus Kc divided by tau I, integral of the error. In terms of the Laplace domain, that will be P of S is equal to, what would that be? You remember the Laplace transform of Kc plus 1 over tau I S multiplied by epsilon. Okay. Because the Laplace transform of a constant plus the Laplace transform of the integral. Integral is 1 over S. Okay. So this would be the transfer function for a proportional integral controller. And this tau I is just defined as an integral time, but it's basically a parameter that controls how the integral response is. Any questions on that? Yeah. Thank you. Yeah. That's what I wanted to point out, and I missed that. The Kc appears in both of them. So actually, you would write this as Kc times 1 plus 1 over tau I S, something like this. Okay. Times epsilon S. Now, what does this mean? Graphically or pictorially, can I get an interpretation? Okay. So here, a PI controller. How does the signal from the output signal P from the valve to the valve, okay, the pressure that I'm applying to the valve, how does that change with time if I have error with a certain known pattern? Okay, so I'm putting a step change in the error, and how would the output from the pressure signal look like? I have the equation for this. Okay, this is the equation. P equals Kc times 1 over tau S. That's what, yeah, sorry.
And I have a question with the Kc times 1 plus whatever tau.
Yeah.
You have that whole, never mind. I just wrote it wrong. What do you say for the transfer function for the what?
For the controller, PI controller, proportional integral controller, which takes an error signal and sends out a pressure signal to the valve. Okay, any other questions? Okay, so we're just trying to develop an understanding of how a valve works and how a controller works in association with the valve. The PI or PID action is the same for any process. But here we are just seeing how it is applied to a simple valve that is pneumatically controlled. So if I make the step change in error, what should the signal that comes out of the controller to the valve look like? Okay, so I'm claiming that and we can do this in Simulink and plot it out. You will see that the pressure signal to the valve will go like this. And can you understand each part of the response? What is happening? What is happening at t equal to 0 when I send an error signal of unit step change? Immediately the proportional part says, I'm going to send it because this is the first part here. Okay, this part, Kc times error. Okay, so there is a constant error, and so the pressure immediately jumps to this. If you didn't have an integral action, how will the response of the pressure be after that? It will be just like this. Right? This is without integral action. Because you make a step change in error, it makes a step change in pressure, it maintains the pressure constant. Okay? And that will make a change in the flow rate, and the flow rate will affect the process itself. Okay, that is governed by the process dynamics. But here we are saying that there is an integral action. Okay, so the integral action basically accumulates because it's an integral of the error. If the error is constant, what is the integral of 1 dt? Error is 1, right? So what is the integral of 1 dt? It's simply t, right? So it increases linearly with time. Okay, and what is the slope of that linear increase? It's Kc over tau I, because that's what we have, Kc over tau I. You see it here. Okay, so all we're doing is in epsilon we are putting 1 and carrying out the integration and plotting the net effect in the time domain. Now, would that kind of an action be realistic in the sense would you expect it anywhere? You will never maintain the error. The idea is to drive the error back to 0, right? So there is some process disturbance that introduces the error, and the control action should act in such a way that the error will be driven back to 0. Okay? So this will never happen in any real process. This is just for us to understand where are the contributions to the control action coming from. There is one contribution that comes from a step change that will remain constant if the error remains constant. That is the reason for the offset. There is no way that you can remove the offset in a truly proportional system, because if the error is there, the control action is constant. The control action is not increasing or decreasing to get rid of that offset. Okay? So it finds its own equilibrium position, and that equilibrium position will depend on the magnitude of Kc. Okay? And so that is the reason for why the offset exists. Now, the integral action, why is it able to get rid of that offset? The integral action says, I'm going to continue to accumulate the error, and that is what its action becomes more and more aggressive. Okay, an integral action continues to send a stronger and stronger signal. If the error doesn't go to 0, says I'm going to increase even bigger pressure. Okay, opening it or closing it, whatever that calls for. Do you understand that conceptually? Okay, so the purpose of the integral action is to provide more aggressive control action. If the error is stubborn and doesn't want to go to 0, the integral action will always say, okay, I'm going to keep on sending stronger and stronger signals until the error starts going down. Yeah.
In a real process, exactly, the error would start decreasing, and then each time that it calculated another KP and then the integral action, or is it just
in a PI setting, the controller will calculate the net effect of both proportional and integral action and send the output. The output from the controller is the P, the pressure signal to the valve, right? That is the summation of both the proportional action and the integral action. But it is the integral action that's going to take care of getting rid of the offset. The proportional action, what does that do? It determines the main time constant. How fast is the system going to go back to its steady state? The Kc. The Kc basically does it controls the time constant. So it makes the response quicker or slower. So you would tune KC, the proportional controller, to adjust the time response, and then adjust the integral constant to adjust the offset. Okay, so you want to bring the offset to 0. Any integral action, however small, will get the offset to 0, but it may take a long time. So if you make tau I larger, then it will bring the offset to 0 quicker. That's right.
When decreasing tau I makes it what?
Oh, sorry, yeah, it's in the denominator. The control, if you want to increase the integral control action, that means you need to make tau I smaller because it's in the denominator. Right? Okay. Any other questions? What do we have next? Yeah, these are basically explanations of what I was talking to you about and how the transfer function looks like. PID controller, I guess we will talk on the next lecture when I come back. Okay. So you can always reach me via email if you have any questions as you're studying for the exam. Okay. Help each other out as you're studying, but if you have questions, feel free to email me.